Hello everyone, I'll be presenting to you 3 projects that I've been working on in the past year in the Global Meteor Network with the accent on using the convolutional neural networks. Let's start first with the GMN MeteorNet project, which is about improving the meteor candidate filtering that RMS uses. So RMS uses a neural network as an additional check in case a meteor detector detects some false positives. The problem is that even then, it can still mark various artifacts on images as meteors. And what can happen is you see this line, which might look at first like a meteor, but when we zoom it out a bit, we can see that it is probably some bug trail that it detected as a straight line. So the goals of this project are to increase filters' capability to correctly discern real meteors from artifacts by training it on a newer dataset of images, and also to explore various model architectures and compare their performances to the currently used model. So here is a dataset that was used. For the start, I used 10,000 images of a much larger dataset from the GMN server. Detections were padded with 20, 50, and 100 pixels, and then results were compared. Convolutional neural networks can only work with a fixed image dimensions, so all images had to be resized to the same dimensions. And 3 of the dimensions were chosen and also later compared to see which one yields better results. And all pixel values on images were scaled to 0 to 1 ranges, as they usually work better with the AI models. For the metrics, F-beta score was primarily used since we can add an accent more on false negatives so that we reduce the possibility of losing some meteors, since that matters more to us. Accuracy was avoided since it isn't a good indicator of the model's performance when dataset isn't balanced, and we can't prioritize false positives or false negatives from one another. That metric looks the same at both of these. I also use for the models hyperparameter tuning, which means the algorithm chooses the optimized values of various parameters like image sizes, normalization layers, and presence of summer layers. And for the training, for all of the models, 20 training epochs was more than enough. And for the training, 80% of the dataset was used, and the rest of the 20% was used for validation. Here are the results in 2 tables. In the first table on the left, you can see all the architectures and their performances in 3 columns for each image dimensions that were used. And on the right is the number parameter of each of the architectures used. More number of parameters means greater computation times for the pies. Here are some examples of mislabeled images. On the left, false negatives, which are meteors that the models usually may have mistaken for some artifacts, and on the right, false positives, which are mostly bug trails, airplanes, or various other artifacts, and there was usually more of them than false negatives. This is the model that currently works the best. When compared to the original model, it has a dropout layer with additional convolutional and max pooling layers with only one dense layer. This is its F-beta score, and its number of parameters is a bit higher than the current model. And this is the current model. With the currently used weights, it achieves a bit lower performance than the model that I have used. And when it is retrained on new data and new weights are acquired, then its performance is similar to the model I currently have. So in conclusion, models achieved best performances when median image dimensions were used. F-score is a preferred metric for unbalanced datasets. Padding of 20 pixels proved to be the best. Model that we currently use in the RMS has inferior performance with its older weights when compared to some newer models. And since models have to be deployed on Raspberry Pis, we need to carefully pick the balance between performance and parameter number. So in the future, I plan to add more sorts of images that were wrongly classified, increase dataset size if it proves needed, and improve performance scores in general. For the tools, I use Python programming language, TensorFlow framework, and Keras tuner. And if you are furtherly interested in the code beneath, you can check out my GitHub repository. Now for the SpriteNet project, sprites are atmospheric phenomena that have not yet been thoroughly researched, and in researching them, data from GMN cameras can prove very insightful, and it can show us how and when do these structures form. But to fully utilize this data, it is not enough to just detect if an image contains a meteor or not, but it would also be the best if we could detect where on images these sprites appear, and machine learning models happen to be the great for this task. I manually labeled over 2,000 images of sprites and have split them into two datasets, one which contains max pixel frames and the others contain detection only. And both of them had rescaled images to 320 pixels. For the model architecture, I decided to use the yellow architecture, which is popular in these problems. I choose a smaller model because we need to take into consideration that this would be deployed on Pis and they would do the computations. You can see below the image how a training command looks like, in which we specify the number of parameters like epochs, image sizes, and batch number. For the training results, when both datasets achieved similar performances, and 250 epochs was enough for most models to achieve their peak performances. For the model implementation, since RMS also uses TensorFlow Lite module for meteor filtering, it can also be used for these sprites. Output of the models is processed in order to get the bounding boxes that we desire, which surround the sprites on each images. And also you can see here the SpriteNet repository if you're interested. For future plans, I plan to expand the dataset and the number of images with no sprites, since that way we reduce the number of false positives. And I plan to furtherly experiment with the model parameters. Now for the third project, this is a project that I did for a college, and it is a UI and UX design of a hypothetical mobile application called the GMN Station Monitor. The idea is that it offers a personalized monitoring of camera stations for the users and would notify them via push notifications if something goes wrong, camera doesn't upload or calibration has some issues. And this way we can have much less downtime. And this is the link to the project file and the QR code which you can scan to test the prototype. And just to clarify, there is no backend or front-end code. This is just simple design, and you can navigate between the screens to check out how the app would actually look like. And this is the showcase of some of the screens that I've designed. So the first one would contain all the cameras that you're interested in. You can also add them more if you want. On the second, we can see the detailed information about each camera's latest session. And we can also get the link to the currently Global Meteor Network's weblog for that night. And you can adjust your alerts that you want to receive. Do you want for regular upload or only when upload fails, or for all station statuses, and also optionally option to have a profile and to back up your data when you transfer to a new phone. So I have to have also special thanks to Paul Rogermans for labeling Meteor dataset, Denis Vida for providing the dataset access, David Rollinson for Meteor model feedback, Sandy Barisic-Shagota and Armir for providing sprite images, and also to my college professors Sanja Čanderlić and Ivona Franković-Lucic for mentoring the GMN Station Monitor project. That will be all from me. Here is also my email if you later happen to have some questions or feedback about any of these projects. And thank you for your attention.
Amazing work, Dino. So I think I'm going to ask a question that's probably on everyone's mind, and that is, when are we going to see these features in RMS?
For the Meteor app, I would like to, again, improve some metrics, but I don't know when I would add them. I would want to maximize the performance as much as I can before actually implementing it as it will be deployed globally, so I have to make sure that it will work in all scenarios as we expected, and that it would yield better performance than the current model. And the SPICE project is still in development. I want to expand the dataset further to increase those metrics as well. And for the application, it is however the community seems fit. Do they need it? This is just a fun project that I did for the college, but if it actually proves useful to many of the Global Meteor Network station owners, I think it can also be realized, since for the backend this is mostly a web scraper, and the frontend is for the design part, it is already done.
That's amazing. So Luke has a question. Luke, go ahead.
Hey, amazing job, Dino. Are the weights combined in one? Is it one pass detecting the meteors and the sprite, or are they completely different projects? And would it be possible to combine the detection in one pass to get meteor and sprite detection?
I've also tried to use the YOLO network for meteor detections, but it has much more parameters than the currently used models, so I'm afraid that it would add too much load, since meteor filtering is, I think, done during the night, and it needs to be fast. And I think that if we can choose some lower models with lower number of parameters for the YOLO network, but I think they're still too high if we want to balance out performance and usability with the accuracy of the model. So for now, I have these two models. One is the YOLO network, and the other one for the meteors is much more simpler. But it also achieves a great metrics, 0.97. It is for now really good. So I think
it's amazing
that transitioning to YOLO network would yield more of the stress for the pies than the actual gain of accuracy.
Makes sense. Thank you.